Hello, students of science. In this video, we're going to talk about nuclear fission and nuclear fusion. So let's start with nuclear fission. With nuclear fission, anytime you have a nucleus of intermediate mass, those are going to be the ones that are most stable. If you have a large nucleus, that one is going to want to break apart. Fission is where you have a single large nucleus that is going to break apart into smaller ones. We call that fission. It's almost going to fizz. In nuclear fission, a large nucleus splits into smaller, more stable nuclei. When it does this, of course, it releases a large amount of energy. A chain reaction is where the product of that initial reaction is going to cause another reaction to occur. So let's say we have this one right here splits, and it's going to split into two smaller ones and release maybe another particle, and that one causes another one to split. We call that a chain reaction. Dominoes would be an example of a chain reaction. The notching of the first one causes the next one, and so on and so forth. So let's say I have uranium-235 gets hit with a high energy neutron that's trying to split into two smaller nuclei. Energy, of course, is going to be released, and that's going to release more neutrons. Those, in turn, are going to split and hit more large nuclei, and of course, causing a chain reaction. The initial reaction causes another, causes another. We say the amount that is needed for that reaction is called a critical mass. That's a chain reaction that is self-sustaining, and once it goes all the way to completion. We would say this is a subcritical mass, not enough for it to actually split. This is critical mass, enough for that initial chain reaction to start another one, so you're getting more coming out than you had going into it. Now, everything to the left of iron here, the only way you're going to get energy from that is with nuclear fusion. Anything to the right, we are going to see nuclear fission. So we are talking about large ones that are going to break down, and think of the higher it is on here, the more stable it is. So remember, iron is going to be our most stable. So uranium, in order to become more stable, is going to break down into smaller and smaller nuclei. So what we're talking about right here is fission, everything to the right of iron. Nuclear power is, of course, where you're going to harness that energy. An uncontrolled nuclear chain reaction releases all of that energy at once, resulting in a large explosion. This, of course, is the atomic bomb, where you get very large mushroom clouds and all that energy is going to be released at once. These are the different ways you could get an atomic bomb here. This is called the gun-type assembly method, where you have two subcritical pieces of uranium-235 that get slammed together to form a critical mass, and that explodes. This, incidentally, was like the one that was dropped over Hiroshima in 1945. Now you could also do the implosion, where you take plutonium and you compress it with very, very concentrated explosions that are almost like lenses that focus it. And so you take what would be a subcritical mass, and then when you compress it with explosions, it becomes a critical mass. This is like the one that was dropped over Nagasaki, Japan in 1945. The end result is the same, a runaway chain reaction causing a very large release of energy all at once, but of course there are different ways to get to that. Nuclear power plants, on the other hand, those are engineered to release the energy, all of this right here, however slowly over the course of decades, so you can slowly harness and release that energy and not just destroy everything. Nuclear power plants are set up so that all this energy sort of bleeds out and drips and drabs over a long time, and hopefully you should not see this over your nuclear power plant. Nuclear power plant has a couple important parts here. Here's a rough cutaway or schematic of the actual reactor there. Of course, you have the fuel rods. Here I have indicated those right here. This is going to be your fissile material, something like the uranium-238 or uranium-235. That is the fissile material which releases the nuclear radiation as heat. So a lot of heat going to be coming off of there. Now you also have these control rods, which can be inserted between the fuel rods. When it does this, this is going to be absorbing the neutrons without causing a chain reaction. This will slow or completely stop that nuclear reaction. We also have a coolant or a moderator. We can see this liquid that's going to be flowing through there. So it's going to be picking up heat off of there and cycling it through here. And it's, of course, going to heat up the water that you're pumping in. So that coolant is going to heat up the water, which then cools it back down, and it goes back to the nuclear reactor for more heat. And then finally, you have shielding. This is going to be the radiation absorbing material that surrounds the reactor. That's going to decrease your radiation exposure. Remember, what we're really worried about here is going to be the gamma radiation. Alpha and beta radiation, very easy to block with either, skin or paper or aluminum foil. The gamma radiation are the ones you need to worry about. They are the least damaging, but they are the ones that are most likely going to penetrate through the reactor. So you need to shield those with a lot of lead and concrete. So shielding, mostly there to protect against the gamma rays. Alpha and beta particles are more or less easily blocked. Here you can see an animated version of a nuclear reactor. So we have water being pumped in through here, and it picks up the heat. That heat, of course, turns the water into steam. The steam turns a turbine. The turbine is attached to a generator, which is a magnet wrapped around a coil of wire, and that creates electricity. Inside the reactor, here I have my fuel rods and control rods. That is determining how quickly the reaction is taking place. By inserting those control rods, you're going to slow it down. Taking them away, you're going to speed it up. And that's where you're going to be getting all that heat generated. And of course, there we have the coolant flowing through there, carrying the energy from outside the actual reactor stuff to our water. Nuclear fusion, on the other hand, works off of a different principle. Nuclei of intermediate mass, of course, are the most stable. So if you have a small nucleus, they actually want to fuse together. Nuclear fusion, small nuclei join to form a heavier, more stable nucleus. Fission, you have one that was breaking apart into two. Fusion, you have two small ones that are joining to form a larger one there. Both of them, of course, are trying to reach that intermediate mass, iron, of course, being the most stable. This is going to release a very large amount of energy. If we were talking like something like a hydrogen bomb, deuterium and tritium or other isotopes of hydrogen are being joined together, release helium and neutrons, and a lot of energy is going to be released for that. That would be a hydrogen bomb, which needs temperatures so hot, an atomic bomb has to be used as a trigger for it. All stars, including our sun, are undergoing nuclear fusion, creating helium from the smaller starting hydrogen molecules. Any star you see in the galaxy is undergoing nuclear fusion. Some of them are going to be going hydrogen to helium, some of them are going to be going helium to lithium, or other such stages in stellar nucleosynthesis, but all of them are trying to form a more intermediate size molecule that's going to be more stable. We have not been able to do fusion on Earth as a reliable source of energy yet. We have been able to do fusion, but currently, as I say this in 2016, there is more energy going into it than coming out of it, which is not what you want in a reactor. But they're working on it, and someday they might do so. That will solve a lot of our energy problems. So, fusion is anything to the left of iron that wants to form this intermediate-sized element there. Anything to the right of this, nuclear fission is going to take place where it's going to try to form that. So remember, both of them are trying to get to here. Fusion, of course, they're going to be taking smaller ones into larger ones. And of course, fission, they're going to be taking larger ones, trying to make it down into smaller. With the peak being iron. Once it's there, it's stable and it's not going anywhere.